I want to start. I just want to talk a little bit about the exam format. So your exam's going to be broken into 3 parts. You can work on them all at the same time and go back and forth between them. The first part are going to be true and false questions. So I'm going to give you a statement, and you need to decide whether it's true or false, and then give a reason. So if it's true, you should try to explain how you know it's true. And if it's false, you should provide some kind of a counterexample or some kind of a reason as to why you know it's false. They're 1 point each. There's 25 of them. You can earn a maximum of 10 points from that section. So you don't have to do all, do you have to do all 25 of them? No, you can do as many as you like.
I have a question.
Yes.
So hypothetically, if you say true but give that correct statement,
I would not count it.
Alright, so
Yeah.
Not even like half?
Not even half. It's either going to be the explanation's good enough or not good enough. Not on the true and false.
So we could do all 25 and get 15 wrong.
You could do all 25 and get 15 wrong and still end up with max points for that part. Okay? Part two is going to be just regular old like homework questions. So they're not multiple part, they're not based on something else, they're just like, do this, do this derivative, like find these critical values, do this limit, show this is continuous. So it'll just be like single question, one thing to do. They're going to be worth 1 to 4 points. So if they're an easy thing, maybe it's a 1 point question, 2 point question, 3 point question, 4 point question. There's 41 total points available in this section. You need to earn 15 of them for full marks. That's the most points you can earn from that section is 15. There's 41 points available. You can pick and choose what you want, what you feel best about. Do the stuff that you know first. Skip the stuff you're unsure about. Your job is to try to collect 15 points from that section. Right.
These questions, are there partial?
There would be partial credit for, if it's a 4 point question, obviously there's like 4 things that I'd be looking for to see along the way. If you get like 2 of them, I'd give you 2 points on that, for sure. Lorenzo. There is no way you could finish every single problem on the exam.
Should I put money on that?
You're going to want to be discriminate, be picky about the things that you spend your time doing, because there is way more questions than you have time to do. Tessa.
So like in theory, if we did all 15
Correct. Yes, that's what that would say. Part 3 are going to be like multi-part questions, like a free response question that you've seen before. Again, there's going to be 5 of these multi-part questions. There's 48 points available in that section. Again, the point values for each part would range from 1 to 4 points. Your goal is to get 15 total points from that section. So again, you can be discriminate. You can pick out the things that you are like, hey, I know how to do this part. Let me do this part. Like you can jump around. You can pick and choose what you can do, what you feel confident about. Your final grade is going to be calculated by your part 1 points plus your part 2 points plus your part 3 points divided by 40. Okay? Jacob.
Do you think the best way to study?
Yeah, I would think that looking at your old tests would be a really effective way of going about it. The other piece, though, that I'd want to be is notice there's no multiple choice here. I've replaced that with the true and false because they're a similar skill set. Where are all the conceptual questions going to live at? In the true and false, right? The multiple choice conceptual questions are now going to be repurposed as true and false questions, where I'm going to ask a little bit more of an explanation from you. But the goal of the game here is collecting points, right? You can jump back and forth between the sections. You have your calculator the entire time. You can use your calculator through the entirety of the test.
How long do we have?
It's a normal 80-minute or 85-minute period or whatever, I think. Back.
What would you say is the best way to study for the true false? Just like memorizing the definitions?
So I would think about concepts, right? Like, for example, a question might be, if f is continuous, then it is differentiable. True or false?
True.
That is false.
Not necessarily.
If it's differentiable, then it's continuous.
The converse is true. Talika is correct. Your counter example would be like, what about a graph that looked like this with a sharp corner in it?
That could be it. I could be like, what about this?
Yes, done. You say false and then draw the picture. If f looked like this, that's it. Sure, you could draw a picture to explain how you know it's
I
false.
could just graph. I could just put some graphs and like false.
Yeah, that would be fine. Again, if you provide a counterexample of a case, there's an f that's continuous but not differentiable. That's good enough for a false. You provided a
But
counterexample.
what if it was the other? Like if it was like if f is differentiable, it's continuous. You'd be like true, and then what would you say? Like,
Well, that's one where that's a fact that we've learned. So you could cite that this is a theorem that we've learned in class.
Yeah, can I just say true, this is a theorem?
You could say that in that
Okay.
for that particular case, because proving that is not something we actually proved. We didn't necessarily even really talk about why it has to be true. Differentiability implying continuity. But that's one that we've used that statement we've used over and over and over again. You can just cite that as that's a theorem we did in class.
Will there ever be like a true statement? You have to prove it on this true?
No, but you should come up. I noticed that the directions don't say proof. It says give a reason or a justification. So it doesn't have to be a proof. And in fact, I probably wouldn't ask for something like that. It would be like you could cite, a theorem. Like if I give you something that basically, that's just the intermediate value theorem. You could say the intermediate value theorem guarantees this to be true, or this is just the intermediate value theorem. Right? You could just say that. True, that's the intermediate value theorem statement. Done. You could do that. That's fine. The true ones I have a much lower standard for why you know it's true, because most of these things are going to be like, that's a definition. That's a theorem. That's a, whatever, a derivative rule. That's just a chain rule. You could say that, right? Like the false ones are the place where I'd be more picky, because I'd really want to see the counterexample or the reasoning you have for knowing it's false.
Like you said, the general, so that one, the question is why is EDPIs particular? Or we just say it's why they're the same thing, just say that's the chain rule.
Yeah, I mean, you could, it would be depending on the question, sure, yeah. Elena.
say it's true, but then our reasoning, or if we say it's false, our reasoning's kind of there, just not good. Is it just zero points on that?
I'm not gonna do any partials on the true and false. It just your reasoning has to be good enough.
Okay.
Whatever that is for the particular problem, you have to be
Okay.
close enough for me to count it. But I'm hoping that with 25 of them, you can find 10 you feel pretty good about.
Yeah. And then our effort for regular questions too, is it gonna be like the regular questions on the test where it's you might get knocked down a point, but you can still get the other three?
Right, so if it's a 4-point question, there's gonna be probably 4 steps I'm looking to get through correctly. If you do 2 of the 4 things to do that, then you would get you get partial. If the question says find the critical values for this, I'd give you a point if you got the derivative correct. I give you probably a point for setting it equal to 0. And then solving that correct is probably doing the solving correctly and getting those values is a point. And then looking at where the derivative is undefined and finding those x's is probably another point. So that's it. So if you do some of that stuff, but you don't do all of it, you can get some of those points, kind of thing.
And then last big question, is the 4, 5, 2, 4, 9 stuff we're doing right now going to be more like predominantly on the test compared to like other sections?
I would say that it would be relatively evenly weighted.
Okay.
So I don't think that the new stuff we're doing now would be overrepresented, or underrepresented is probably about fairly represented. Like you'd see a question or two probably coming from these sections, you know.
You guys do on Friday, we took our test.
We talked about 4 or 5, which had no new concepts in it. It was just like, how can we use calculus to create a picture of a function that we know nothing about? Beck.
Time-wise, would you, like, how would you suggest we break it up? Like, what do you think will take the longest to get the points?
So Beck is asking, what do you think is going to be the longest to get the points? That's probably going to vary from person to person. My suggestion to you is just read the question. If you know exactly what to do immediately, do it. If you don't, skip it. And just go through the test at least once, just doing everything that you know as fast as you can, and then come back and be like, okay, I'm like, you know, I'm definitely at least 3 questions short in this section, or 5 points short in this section. Like, let me spend some time on maybe a maybe, you know, like maybe circle some of the maybes. Like, okay, I think I could do that, but I'm not sure. I'd have to work at it a little bit. That would be my strategy. Yeah, is I want to get like, yeah, I just want to, time is going to be the trick, right? You know, if time is unlimited, that's a different story. But here it's, you know, you have 80 minutes to collect as many points as you can. I'm going to collect as many points as I can. You know, obviously if I do, I'm going to be kind of mindful the first time through. Like, I don't want to do 20 points in the true and false and eat up half my time, right? So like, after I've done a lot of them, at some point I'm probably just going to quit and go to the next section or whatever.
Okay, thank you.
But that would be my general strategy, is just make sure I do everything I know how to do while I have time. And the stuff that I think I know what to do, or I'm not quite sure what to do, but I think I have an idea, that stuff I want to wait on.
Well, I mean, we could get partial credit from all of the
Absolutely.
regular, so we could
Yes.
do just like part of each one and keep moving.
Yes.
Yeah.
Yes, absolutely. Absolutely. Do we feel comfortable about the format here, Pierce?
Didn't you say that you do like the AP system for the finals?
Well, that's this, like, think about what's on here. We have 25, 41, 48. That's like, what's 89, 114 points. You need to get 40. So
Oh, I get it.
there's 114 points, I think, if I count those up. You need to get 40 of them.
Same, because I have partial credit.
Do we get extra credit if we complete more than?
No.
I will grade until you get to the most points you can get out of that section. So like,
You need a 30. If you do the whole test, you get 35%.
yeah. But here's the thing, Tessa. There's no way you have enough time to do the entire thing. Like, it's just not going to be realistic.
I mean, why are you making that face?
But that's what I just want to, like, are we okay with, we okay with the format?
Yeah.
Seems fair.
Yeah.
So when we get all 3 parts of the same.
You get it all at the same time. It's just all stapled together. It's going to be one thing. It'll just have like part 1, part 2, part 3. It'll be a lot of pages, sure.
So if you just do really long true and false and like then on like the next 2 parts, you still get 100.
You get 35%.
No, you need
No.
15 points for each section.
No, it's 10 from true and false, 15 from the other 2,
Yeah.
right?
You get 25 out of 25
On the true and false,
15 of them just don't write.
all you get is 10 points, even if you got 25 of them
Why
right.
don't I use 25 dollars? I need a question.
Okay. Is it clear?
Mr. Flick, how would you recommend studying for the true and false? Just like going around the theorems?
So yeah, theorems, vocabulary, like facts that we use to do problems, like the relationship between the first, second, or function, first derivative, second derivative,
Okay.
like those kind of relationships I think are all important.
Okay.
You know, like It's all kind of like the conceptual pieces.
You should always explain the true ones also.
At least some kind of justification, even if it's just like, oh, I'm just using the intermediate value theorem. That's just the intermediate value theorem, right? Or like, oh, that's just like, what, because it's continuous or whatever.
And then would you say like the test, like past tense, is that like where it's gonna be like mostly like drawn from?
So the problems, like the regular problems, are going to be a lot like homework problems, or just like the regular test questions that aren't multi-part. The true and false would be most like the multiple choice, where it's like a conceptual thing. In fact, there's even like on the multiple choice, there'll be questions like, which of the statements is true or false? Like it's kind of like that. And the multi-part questions are going to be like the free response questions we've seen on the test or in the practices that we've done.
Like we'll say like past tense and like the practice.
Yeah, I mean it's kind of everything, but I would spend less time. I would spend some time collecting the theoretical stuff, like the facts and the theorems, and like the vocabulary. Make sure I'm feel pretty tight on that, and not only like what does it say, but also what does it look like, right? Like what's the picture that kind of describes what's going on here? That'll often be really helpful as a way to generate a counterexample or be able to tell quickly whether something is true or false. If I kind of like, okay, this is what it's saying is going on. Does it have to also, this thing have to happen? No, because if I drew it this way, like a lot of questions you could answer that way, where you have to think about like, what does it look like? But then the regular problems, I would think like, okay, what did the homework problems kind of look like? Like, can I take a derivative that involves a product rule and a quotient rule at the same time or something? Can I do, like stuff like that? Can I do the limit of something that involves L'Hopital or not a L'Hopital situation? Can I do something like that? And just kind of review some of that stuff. I wouldn't like get bogged down until I've kind of gone through and been like, oh, I'm kind of shaky on that. I should do some practice there. But that's what I would do as a first overview. And then the multi-part things are going to look like, like the hard questions just kind of broken up into pieces. That's essentially what all the multi-part questions are. It's like, could we have asked this all at once as like one super question, or did we break it up into like a little bit more chunks to be able to do some stuff?
Like studying for after our past FRQ is similar to really going.
Yeah, and the FRQ questions from the previous tests. Yeah. Or even like, like I could take a part of a previous test FRQ and just make it a regular question, right?
Would there be any times for like the regular question or the multi-part where you'd be like specifically use this from like 2.1?
I might give you like a hint as to like how to do something. Like I might tell you like, show that this is continuous by doing blah, 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 blah. And like tell you how I want you to do it. But I wouldn't like over micromanage how to do one of the problems unless I thought there was like a Weasley non-calculus way to do it.
It's a very first question. We could like low-key tolerate.
Absolutely. Yes, absolutely.
And if we were to retake that first test, could we use our new tricks?
Ooh, that's an interesting question. I have to think on that.
Okay.
Okay. You give me like, send me an email and I'll make sure I get back to you. But I want to think on that for like a little bit of time. Yeah, Braden.
So you were saying that a lot of the true or false is replacing the multiple choice.
Yeah.
I was looking over the MCQ answer key. And there's some should I use that to help study for this? And if I am, should I study mainly the ones where you're like explaining it rather than just like putting it?
So yeah, when I do the MCQs for you guys and I write an answer key, I try to come up with some kind of an explanation for everything that gives you some clue as to like, what was I thinking when I did this? because we don't have enough time in class for me to like do this verbally the whole time. So I try very hard to find ways to do that. I would say in general, the true and false are going to be a little bit shorter than a lot of the MCQ things. In particular, because you can pick and choose the stuff that like, oh, like I see what to do immediately with this. Like I know exactly what's going on here. Or I recognize this is like, oh yeah, that's the loophole here because that's the mean value theorem, but you didn't give me differentiability or something. So all I have to do is draw a picture where like, you know, like it's not continuous or something, or, you know, has a corner in it or something, and I can give you a counterexample to that really quickly. So I would say more so I would collect, you know, like your theorems, your vocab, your stuff, and I try to think about different representations. So like what would this look like with an equation? What would it look like as a picture? What would it look like as a table? And like try to think maybe that way as like, okay, how can we like, what is this saying in these different forms? I think that's maybe the better preparation than necessarily like drilling specific MCQ questions, because they're not going to be like, yeah, just not the same. It's the same skill because it's like just conceptual with no calculation. Your calculator is going to be, I would think, relatively useless. But, you know, much like a lot of the multiple choice where even if you have the calculator, it's like I didn't use it. Yeah. Jacob.
The 4.5 stuff because of the day, would we expect that?
I think that like a part of a 4.5 question would make a fine regular question, or like if it's a multi-part question, like some of those steps along the way would be a fine, like would make a fine multi-part question, right?
So we should know it?
Yeah, you should be able to know what those things, at least what they're giving you. Like if I want, you know, like if you take the first derivative of something and how do you find the things that are increasing, decreasing? You know, like how do you find the mins and maxes with it? Like 4.5 was just basically we re-summarized what we did in 4.1, 4.2, and 4.3 with a little bit of stuff from algebra. You know, like, so I don't know that like it wouldn't necessarily ask a bunch of 4.5 stuff because so much of it is just like 4.1 and 4.2 and 4.3 stuff also. Does that? Okay, back.
Since we're not doing a unit test for the last two sections, do you have like a full test or something you can give us to have an idea of what test questions might look like for those?
Yeah. So I would say that a 4.5 question is going to look exactly like a 4.1, 4.2, 4.3 question, where it's just like, you know, like finding mins and maxes, or like, you know, inflection points or intervals of increasing, decreasing, or concavity, just like we've done in those sections. Like, I don't think that there's any calculus things that's going to be any different as a 4.5 question. For 4.8 is one idea, and it's like, well, Newton's method is a way to create an approximate solution to like a polynomial or something, and that's all I would ask. You know, just like the homework questions are all identical. It's just like one kind of question. You know, the optimization stuff, which was what I want to talk about today, is all application. There's no new concept at all. So just like, you know, like there are kind of any homework problem would be a fair exam. You know what I'm saying? So like these last three sections are very like, it's just like the homework would be what I would give you. Like I wouldn't ask you anything weird or different. It's just like it should look like something we've done in the homework. If that makes any kind of sense. All right. We need to start doing something here. We've talked about this kind of enough. I hope you guys feel a little bit better about what I would ask you to do. Today we're going to talk about these optimization problems. Different kind of optimization, but like optimization just refers to like finding the best way to do something. Now the methods that we're using here are going to be different than those combinatorial optimization problems that I showed you from a grad school homework. So here, if we look, there's like no new concepts here. This is all just kind of using your first and second derivative rules like we've done before. Because what is a optimal solution? It's going to be like the best way to do something or like the cheapest way to do something. It's going to relate to a minimum or a maximum. So all the techniques we've used in 4.1, 4.2, 4.3 for finding mins and maxes are going to be the tools that we're going to use to do the optimization. What makes this tricky is that it's going to be built into a story problem. So it's going to be like an application-driven situation. So it's kind of like the related rate problems in that regard, where it's like the calculus is no different than anything we've been doing. The hard part is like unpacking the calculus from the situation, right? So what I have listed here are just some problem-solving steps to kind of keep in mind while we're doing this. So the first step is you want to understand the problem. You want to read carefully until you clearly understand it. If that means you read the problem 2, 3, 4, 5, 10 times until you really understand what's happening, then read it over and over and over again. While you're reading, you want to ask yourself, like, what are the unknowns? What are the givens? What are the conditions going on? Like, is something, is one dimension fixed or something? Stuff like that. Step 2 would be drawing a diagram. Almost all these situations are going to be a little geometric in nature. So having a picture of what you're doing oftentimes is super helpful. And going along with that, like labeling your unknowns, where the unknowns are from part 1 on your picture, or where your givens are, or all that kind of jazz. Step 3 is introduce notation. So you'd want to assign a symbol to the quantity to be maximized or minimized. Typically, the textbook uses the letter Q for whatever that quantity is we're trying to minimize or maximize. And then you want to, select some names for your other unknowns, like a variable, A, B, C, D, X, Y, Z, P, D, Q, whatever. Again, they say use suggestive symbols. Don't be afraid of subscripts, right? Like when we did the related rates, I often did radius of the container, radius of water, and put some subscripts on things to remind myself, like volume of container, volume of water, just to remind myself like what's going on. Step 4 would be write an equation of Q in terms of your symbols from step 3, your knowns and unknowns. If Q is expressed as a function of more than one variable, you're going to want to eliminate a variable, kind of using the same kind of techniques we did for the related rate problems. Oftentimes, you're going to be building a similar figure, much in the same way. And then after you've eliminated all but the one variable, they say write down the domain of the function. Why is that going to be important? Because once we have Q is equal to f of x, that equation, we're going to take the derivative of it and find the critical values. So we need the domain of Q so we can compare the domain of the derivative to the domain of Q, because we need those possible critical values, right? So the domain is going to be important because it's going to help us when we look for the critical values on the final step. So part 6 says, use the methods of section 4.1 and 4.3 to find the absolute maximum or minimum values of f. In particular, if the domain is closed, then use the closed interval method from section 4.1. If it's open, you're going to have to use the first or second derivative tests from section 4.3, and then with whatever your candidates are for your min or max, plug those in to find the actual values to see which one is the biggest. Okay. So let's do a couple of examples here. So example 1 says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river, what are the dimensions of the field that has the largest area? So when I'm drawing my picture, you know, like here's my river, I might start by just like drawing some hypotheticals, right? You know, like, okay, maybe I have a field that looks like this, where maybe like that's 100 and 100 and like 2200, right? Like that's a possible field or fence you could draw, you know, or you could do like something like this, where it's like, I don't know, like 700 and 700 and 1,000. Oops. You know, there's lots of different shapes you could go. You're trying to find the one that contains the most area. So what are we noticing about the dimensions here when we draw these rectangular fields? Those two sides are the same, but the other one is different, right? So the picture that I'm going to draw then, oh goodness, fight with me today, huh? And label, I'm going to call this like length, width, length. And then the insides are going to be my area. Does everybody feel okay about this? So what is the quantity that we want to, in this case, maximize? Because we're looking for the largest area. So I want to write an area function. So how would I find the area here? Length times width. Now there's a little bit of a problem there, because that's area, length and width are both variables. So I have an equation here for area in terms of two different variables. I would like to eliminate one variable here. What other equation can I write here to do that? What have we been given that we haven't used yet? Yeah, 2,400 feet of fencing. What is that going to tell us? The perimeter. Excellent. Oops. Oh my God, come on. OneNote just doesn't want to erase anything for me today. All right, OneNote, challenge accepted. No more mistakes. Everybody's okay there? So what I'm going to do then is I'm going to solve the perimeter equation so that either L or W is by itself. Which one do you suppose I'm going to choose? W, so I don't have to do any division, because who wants to do division and end up with fractions possibly, even though in this case it would only be one fraction, but like nuts that. I don't want to do that. So I will have area now just in terms of L when I substitute that in. And I would distribute the L through, because my next step is just going to be to take the derivative. And I would much rather just distribute than have to do a product rule, like nuts to that. Like, let's use some algebra and make our lives easier. Are we okay so far? Okay. So that's going to be 2,400 minus 2L. Oh, I'm sorry, 4L. Yeep. Made it like 1 minute before I made a mistake. Not very good, Kulik. Everybody's still doing all right. So before we continue on here, we should have done something before we took the derivative. What should have we done? Not factor. We want to do a domain, right? That's incorrect, because we're talking about a physical situation. So what is the smallest possible L we could have? Yeah. And then what's the biggest possible L we can have? Oh, yeah. 1,200. Great. Well, if L happens twice, right? We have 2,400 feet of fencing, so the most L could possibly be is 1,200. Now, I don't know what that means, zero width or something, so just like a fence that just comes out and then comes straight back. It's like the dumbest fence you've ever seen that contains no space, but like, whatever, that's good enough. If I do the derivative, is that going to change anything for the domain? No, man, it's good, right? Like, this is a polynomial, that's a polynomial. There's no reason that the derivative would have lost anything in doing that, right? Okay. So we set the derivative equal to 0. So when we do that, we get L is equal to 600, right? Pretty okay. Now I need to check here because, or I need to be careful, right? So I know we're operating on an open interval because you can't actually have 0 or 1,200, but you can go like right up to it. So I don't need to check the endpoints, but I don't know for sure if this critical value, the one critical value we have, is a local minimum or a local maximum, right? So we don't know if what we found was the best way to do this or the worst way to do this. There's two ways to check. What are the two ways I could check that? Great. So Braden says you can do the first derivative test, which involves building a sign diagram and testing a value before and after. The other option is doing the second derivative test and looking at the value of the exact point at the second derivative. That's the one I want to use because look at how easy that second derivative is going to be. What is the second derivative? Guess what? The second derivative is always negative. So what does that tell this?
It's a max.
It's a local max. And in fact, since it's the only maximum, would tell us it's also the absolute max.
That tells us it's a max because it's always concave down.
Correct. Yeah, because the second derivative is negative at 600, because the second derivative is negative everywhere.
Right. So it's a max. That's the best way.
And since it's the only max, it's the absolute max. That means it's our absolute best way to do that. So how much area could we contain then? So whatever that is, I'll trust Braden for 72. Let's do it there. That feels easier. Yeah, that sounds better.
I don't know if we should be trusted.
Yeah, I don't know.
Yeah, it's wrong.
Well, no, mine was a reading problem, not a.
It's a speaking problem.
Hey, Mr. Coach.
Yeah.
Well, like, so in a problem like this, why is that like better as opposed to like a different?
Well, that's the maximum amount of area that fence can contain.
Oh, it's like
So
worse would be, like,
you
the
took
worst
you
amount.
took a fixed amount of fencing, and you built the biggest field you could out of that fencing. That's what we're being asked to do. We wanted the maximum area.
So if you accidentally solve for the worst, then how are you supposed to get the best?
You should have, one, you would have needed more than one critical value,
Oh.
right? And then you would have just misanalyzed which one was the max and which one was the min, kind of thing. Jacob.
What's like the logic behind why the highest point would be the biggest area?
So if I'm looking at my area function where like x is L and y is our area, so like that's going to be the L that gives us the biggest A, right?
Oh.
Right, because that's what we have here. So we found the L that gives us the biggest area.
Paragraph second derivative.
This is just A, right? What I guess I misunderstood what you're asking me then, Jacob. I thought you were just asking me how do I know this L gives me is the or that value of area is going to be the biggest area.
I think I was just thinking that what I was doing in my mind. Okay, never mind.
You're okay?
I got it.
Okay. Okay. All right. Next example, we have a cylindrical can that's being made to hold 1 liter of oil. Find the dimension that will minimize the cost of metal to manufacture the can. Great. So we want to minimize the surface area for a cylinder. That's right. We're looking for a minimum. So anybody remember the surface area for a cylinder?
Oh, 3/4 something.
So you have
Oh, it's volume of something.
you have a circle for the top and a circle for the bottom. So those are volumes. We're doing surface area, right? So you have a circle on the top and a circle on the bottom. Plus,
pi r h.
it's 2 pi r h. So it's the perimeter
Right.
times the height. Because when you cut that can open and cut the bottom and top off and you unfold it, that's a rectangle. The height of the can is the height of the rectangle. The perimeter of the circle is the width of the rectangle.
I do remember doing this in geometry.
Now, do I expect you to remember that formula? No, I would provide that for you. Okay. All right. So this is what we're trying to minimize. What's the problem here? Yeah, it's in terms of 2 variables, right? R and H. Okay. What else are we given, though, in the problem? What's the liter giving us? The volume. Great. What's the volume for a cylinder? Great. So I know 1 is equal to pi r squared times height. What's the problem with this 1 liter? It's a unit problem.
Yeah.
Because we want to eventually find a linear length. We want dimensions. We want like lengths of radius and length of height, right? Chemistry people. How else can I write a liter using like, meters or centimeters or millimeters or not? No. I want a linear unit in it, like centimeters. Yeah. It's 1,000 cubic centimeters. A mole is just a measure of quantity. It's like a dozen. That's all it is. So science people, 1 liter is 1,000 cubic centimeters.
Would that be something you provide?
Yeah, how am I supposed to know?
No, I wouldn't have written it as a 1 liter. I would have written it as like 1,000 cubic centimeters.
And you would give us that, most likely.
I would have, again, I'm just stealing the textbook's problem. I would not write 1 liter. I would just have written it as 1,000 cubic centimeters. Because, like, shoot me in the head. Like, I gotta remember more stuff like this. Like, give me a break. All right. So which one do you want to substitute out of our surface area equation, R or H?
I like R. I think get rid of R.
Get rid of the H. I agree. Because if I take this equation and I divide it, I'd much rather not have to square root. Like, get me the heck out of there. I don't want to deal with square rooting anything. That really makes the domain just a royal pain in the...
But yeah.
So far, so good. Do a little reducing. That's right. Now, let's do a domain.
0 to 1,000.
Well, R is a linear distance. Cubic centimeters are a cubic.
Centimeters squared.
So I would just do this. I mean, like, I'm not monkeying around with it. I don't think it'll matter because, again, we just know that R can't be 0. That's probably good enough. All right. So my derivative of surface area is going to be
4, 5.
No, don't do a quotient rule here.
Flip it.
Do that.
Oh, smart.
I've saw so many unnecessary quotient rules when I was grading the test. So many.
How are they looking at
I
it?
do the quotient.
I don't remember doing
Looks
one.
like I know.
No comment is crazy.
I feel like a 1 to 10. What do they got?
We'll talk about it once I've graded them
Oh
all.
boy.
No comment is crazy.
We'll talk about it. I don't remember doing this.
Everybody's okay with how I... Right? Negative 2,000 over R squared would be fine also. Shh. What's the domain here?
Not all real numbers. 0,1007.
Yeah. Still the same thing, right?
Why do we get infinity if it's a defined
Why not?
cylinder?
Because all we really... So if the volume is fixed at 1,000, right? R can be massively huge, and then H can be itty bitty little. And it'll still come out to be 1 liter. Right?
Why don't you have done that with that?
Because the perimeter was fixed. We had only so much material to make the perimeter. Here, the volume is what's fixed. We can make as much, we can use as much material as we need.
So the area was fixed on the other one, the regular wasn't?
Correct. Then it would be infinite. Yeah. Does that,
Yes.
so just like, you actually have to like think about like physical reality, which I know is challenging sometimes because it's like not a math reason. Okay. Now what do we do?
0.
Great, we set it equal to 0. And I'm going to write it this way now. How am I going to solve that? This was an issue on the test as well.
2,000. Cube root of.
So let's multiply both sides by r squared to get rid of the fraction. right? That's I think where we're heading when I heard an r cubed or a cube root. That makes life massively simpler, right? So we add the 2,000 over, divide by the 4 pi, and then cube root, right? Okay. I mean, you probably want a decimal. You can reduce it, certainly, right? That can just be 500 on top. We'll do that. Okay. Do I know if this is going to be the r that maximizes or minimizes our equation? We need to do the second derivative. Okay, what's the second derivative going to be?
Negative cube root of 5.
So you're differentiating this. So 4 pi, and that'll be plus now. Oops, should be 4,000. No, thank you. And this, if r is greater than 0, has to be positive, right? So this is a minimum,
And that's what we want.
which is what we wanted,
Oh,
because it's a dimension of a can.
the real life is really
Real life,
Wait, how does
What are we doing if it's not what we want?
it will be. It'll either be a choice, or you'll have only one thing and it'll be what you want.
Wait, so it would never be like we wanted the max, but we got the name.
I'd find it unlikely that you would end up doing that. But we need to check here.
Didn't we
Right.
notice the minimum before we did,
No,
so we just do that?
we knew it was a critical value.
Yeah.
We didn't know it was a minimum. Could have been a maximum.
So then we solve.
Or it could have been nothing, right? You can have critical values that are neither mids or maxes. Okay, too much talking going on. Go ahead.
We solve, to see if there's a minimum or maximum by.
And doing the second derivative test. Yes. Pierce.
So how come because it's greater, so how does that prove? Why wouldn't that-
That's the second derivative test. Concave up.
Oh, I thought-
Concave up will be minimum.
I thought you said it was next.
Yeah. Beck.
And why did you know that second derivative equation is greater than 0?
Because r has got to be positive,
Okay.
right? Because now you have positive plus positive. So it's got to be positive, right? That's going to be greater than 0 everywhere. As long as r is positive, which is r is always positive. R. Sounds like a pirate with a stutter. So again, I think this asks for the dimensions though, right? So we have r. What do we still need though? H. Whatever that is. That's what I'm gonna do. I don't want any part of that. Like, type in your calculator and get a decimal. But like, you know, do it in 2 steps. Type the cube root first and then ants it in there. You know, that's how I would do it. So again, our observation here, we state this theorem. So if the first derivative is positive for everything at less than some value, and it's negative, the first derivative is negative then for everything greater than that value, then that's an absolute maximum. It's basically the first derivative test with just one thing, right? That's all we're saying. So if we have like our sign diagram, here's C, and everything before C is positive, everything after C is negative, that's an absolute maximum because it's a local maximum, but there aren't any other maximums, so that's got to be the biggest, right? It never becomes increasing again. There's no way to get back higher. It's just, that's it, right? That's all it's saying. And then you can say the reverse is a local minimum, the same thing that we just observed up there. Or is an absolute minimum, excuse me. Is that okay conceptually on what we're saying? Is it saying like, here's C, so if we're increasing up to C and then decreasing everywhere after C, that had to be an absolute maximum. That's all it's saying. Okay?
What if it's like more than one C?
Listen, if it's more than one C, this doesn't apply. It's only for C. Can only be, if you have only one critical value, then any local maximum is an absolute maximum, any local minimum is an absolute minimum. But if you have more C's, then this doesn't apply anymore. All right. Let's see, what do we have here? I'm going to skip this one. I want to do a more geometric one, I think. Is that okay with you guys? We're running short on time. You guys asked a lot of exam questions. I wasn't prepared for how many I was going to get. That was okay, though. Happy to answer them. I'm just going to have to be a little bit more judicious about my exampling here. So a man launches his boat from point A on a bank of a straight river. It's 3 kilometers wide and wants to reach point B, which is 8 kilometers downstream on the opposite bank, as quickly as possible. He could row his boat directly across the river to point C and then run to B, or he could row directly to B, or he could row to some point D between C and B and then run to B. He can row at 6 kilometers per hour and run at 8 kilometers per hour. Where should he land to reach B as soon as possible? Assume that the speed of the river is negligible compared to the speed in which the man rows. So let's draw our picture. So here's our straight river. Here's our point A. Directly across the river, which we know is 3 kilometers, is point B. Oh, sorry, that's not point B. That's point C, was directly across the river. And then 8 kilometers downstream is B. And then he said, or we could go to like some point D there in the middle. And I'll just call that distance from C to D X. And what we want to do is find the fastest route to get to point B. Right? So you could do all rowing right from A to B, right? That's a route. You could do row to C and then run from C to B. That's another route. Or you could do something in between, where you land somewhere in between. You do some rowing and then less than 8 kilometers of running. Everybody's okay with it? With the setup here? Okay. You know who's really good at stuff like this? Animals. Yeah, you ever like have your dog at the beach playing fetch and you throw the ball into the water? The dog never runs like straight in and then swims, and never like jumps and swims straight to it. It runs in and then like will swim to it. Like it knows somehow that like you don't want to do either end. You want to do something in the middle. Okay. All right. So what quantity are we looking to minimize here? Not distance, time, right? We want to get there as soon as possible. Now, in our scenario, how are we going to calculate the time it takes him to do this? Distance divided by the rate, yeah. Just like, like how long is it going to take, if you want to drive if you're driving 500 miles at 50 miles an hour. So, it takes 10 hours. So far, so good? Okay. So what we're going to do is we want to calculate that distance there. Because what we'll find is if we do it this way, that distance, and if the best route is going directly to C, well, X is going to just equal 0, right? Or if it's the best route is going directly to B, X would just end up being 8. So that's the distance we're going to do because that's variable, right? D could be anywhere in between C and B. Braden. Okay. So if I know that those are 3 and that's X, how long is AD? Square root of 9 plus X squared. How do I know that it's not plus or minus? It's a distance. Great. Perfect. Yep. And then how's my distance from D to B? Very good. 8 minus X. Okay. Well, the whole total is 8, and this side, that part is X.
Sorry, I completely blocked out.
So our time function then is going to be the distance in the water, which we can row at 6 kilometers per hour, and then our distance on land, which we can run at 8 kilometers per hour. That's our time function. So far, so good. What's the domain? And that's closed, right? Because 0 for X implies we're going straight across and then running all the way down. If X is 8, that means we're not running at all, we're just rowing straight there. Or vice versa, maybe that's the vice. No, X is 0 is straight across and then run down. X is 8 means we just rowed all the way there. But those are closed because those are options, right? Okay, let's do the derivative. How are we going to do the derivative of that first piece? No quotient rule.
We move it up to this top and give it a negative X.
Just going to pull it out front. We can ignore it because it's constant. And it's a chain rule now, right? So the inside stays the same. What's the derivative of the outside? Great. I meant to leave myself more space there. And then to the negative 1/2, right? Not quite. Yes. Yeah, there you go. The derivative of X squared plus 9, right? Okay. How do I do the next piece?
-1.
Great. -1/8 is correct. Well, this is the way I would think about this. What's the derivative of 8/8? 0. What's the derivative of x over 8? 1/8, right? And because there's a negative sign in front of it. Okay. We need to, again, if we got to tighten up some of our derivative rules, it's been, got to make sure that those are always tight, right? Now, in addition to that, we have to look for the easiest way to do things, right? I think part of our time issue is a lot of us know what to do, but we're taking like really time-consuming routes to get there, which is not wrong. I want to be clear. But it's going to we're going to run into time problems. You know, like if we can't see how to do things quickly, things that are designed to be easy become very hard, right? And we're going to do at least this section. We might spend some time next week talking about how to make things easier. All right. So now we look at the interval in which this is defined. Can this become undefined anyhow? The only thing that changed is now this moved to the denominator. Can x squared plus 9 ever equal 0? No. Not with a real number anyways, right? So the domain should still be the same. So we set this equal to 0. So let's see, let's clean up some here a little bit. So I have x over 6 square root x squared plus 9 minus 1/8. Everybody's okay with how I cleaned up there?
Just 2x over 12.
Yes. All right. So this is pretty yucky here, right? So if you have a calculator, what can you do? Yeah, graph and find the intersection, for sure. If I have a calculator, that's how I'm doing this. Algebraically, could we still do this? Yeah, but it is going to be a beast. So I would add the 1/8 over. And then I would multiply both sides by 48. That'll get rid of the constants in our denominator. And then multiply both sides by x, or square root x squared plus 9. And then we square both sides. Is everybody okay? We'll distribute that 36 through, well, let's just do there's some kind of reducing that can happen there. 4, right? That's going to give me 9 and 16. So I'm going to have 81, and when I subtract that over, that's going to be 7. So x is going to equal the square root of 81 over 7, plus or minus. But we don't want the minus, right? Because x is a length. Remember, x is the distance the distance from this directly across the river that we're going to land. So there's my value. Now, is that a local minimum or maximum? Oh, never mind. Wait a minute. What kind of interval do we have? Closed. So we can just do t of 0, t of square root 81 over 7, and then t of 8. So I'm going to save you the hassle, and I'm just going to write down what these are. How'd I do that? Calculator. I just plugged those into t. So I just, nope, t. Since I have a closed interval, I can do just the absolute maximum or minimum test. So like I just plug them in. The biggest value is the biggest, or is the maximum. The smallest value is the minimum. Which one do we want? We want the minimum, because we wanted to do this the fastest way possible. So we want the smallest time. We want to take that middle landing point, or midway, or in between landing point, I should say. And the time it took is 1.33 hours. Elena. That's okay. I just did the Pythagorean theorem with that triangle there. Right? Is that perfect? Love it when it's easy, right? Yes. Okay. We're at like the end here, right? There's like a couple minutes left. So this is the homeworks. Let me look at these again because it's been a minute. Did I already make the test? You mean the final exam? It is in the proofreading stage right now. So it is, I've basically written it. I just need to go through and do the problems and make sure nothing is like more unexpectedly difficult than I thought it was going to be when I originally conceived it. So it's just like finishing touches. And then obviously if we don't end up covering all of these last two sections left, you know, there would be like a substitution that would have to happen in a couple of places, but that's basically where I'm at with it. So it's basically finished. What's up?
So we probably won't run the what would you do if like you did the second derivative test, like minimum?
So if that happened, you have no solution then. Right, like if we did something and there's one critical value on an open interval, and that critical value was a minimum when we wanted the maximum, then there's just no solution. You can make it as big as you possibly want it to because the other ends have to be infinite. So it's like unbounded. So there would be no maximum.
So there would have to be another zero somewhere.
Likely another critical value. Well, again, be careful. I'm going to say critical value because it could be something where the derivative is undefined.
Right.
Could be a domain thing where you got your other critical value from. And that's probably, if that happened,
Corner, right?
yes, or a discontinuity or something. So if that happens where you get the wrong one, it's probably because you missed a critical value.
Right.
Whether it's from solving you missed it because you divided by a variable or something, or there's like a discontinuity that you missed when you went from derivative or function to derivative,
right,
that we forgot to count as a critical value. It's probably one of those two things.
Okay.
You know what I'm saying? Like if I wanted to minimize
Like
the...
how would you find the where it's no solution for a derivative?
Oh, you just set the derivative, you see where the derivative is undefined at, and just see if it's different than where the function is undefined. So like I'm just, like here, the function is defined for all real numbers because it's polynomial. The derivative is defined for all real numbers as polynomial. Even if we're talking about a subset of that, it's going to be the same subset.
Right.
So like that's all I'm doing to check that is just looking at the domains.
Okay. And if they had a different domain,
Then whatever was missing from F is a yes, exactly.
Okay.
Yes. Now those don't come up super duper often,
Right.
but they can. And if you're getting like the wrong one, that's probably what happened. Now, if we had taken this problem instead of asking to maximize your area, if I asked to minimize the area, there it's unbounded. Like you can make that rectangle as stupidly thin and skinny as you want and get whether you skinnied it this way or skinnied it that way.
Right.
But that'll be like your worst possible shape. And you can make that as skinny as you want to where it's like infinitesimally little area in there. So that's one where there is no minimum.
Okay.
Because what you would have found is a maximum, been like, oh, well, it's concave
I
up.
wanted you to find the most inefficient way.
Yeah, so like so when you get the wrong one, it's either like, oh, I misread the problem, which can happen, or you missed like a critical value somewhere is probably what happened. Pierce.
Can I ask a question again? The last one that we just did.
Sure, what's up?
I just want to know if I read it right before I asked.
Oh, yeah.
Oh, yeah. So it asks you where he should land, but then you just answer.
Oh, where should he land? Okay, so like we said at point D is where we wanted to do.
Okay.
Right? That's what this X is. That's the, that far down river or whatever. That's where we should land. Because it was the fastest time,
Oh, okay.
right?
Do you think we'd be way less likely to encounter like when we're defining fixed values?
When it's, especially when it's geometric,
Yeah.
yeah, that doesn't happen very often. Now, if it's like,
Especially not on our final.
yeah, it's pretty rare that kind of thing happens. Usually these go pretty true to form. The hardest part is usually, in general, for these problems, what's the hardest part? It's usually getting that correct. If you, yeah, what's up? Shh. Yeah, so if x equals 0, that's just the equivalent of doing this, which is an allowed route. If x equals 8, then that's just that route, which was an allowed route. Bray, does that feel good? I think it does.
It's just like really annoying.